This is the analysis of the crank slider mechanism for the power hammer. In MATLAB, essentially what was done was it asks for the dimensions of the crank slider. So it was the length of the first link, second link, the offset, which we aren't using, but it's there if we need it, and the angular velocity of the crank, which we're assuming to be constant. From there, it makes a vector of the angle and an increment of 0.1, and then converts it to radians because that's what MATLAB uses. From there, it's essentially just a bunch of equations breaking down the closed vector loop analysis and solving for the unknowns to be able to get the position, velocity, and acceleration. And then it plots them, and then also returns the minimum and maximum position, max velocity, and acceleration. I thought those would be nice values to be able to reference. Here's the plot that it generates. And it's hard to see how much of the distance is changing just because we have 100 radians per second, or sorry, 100 revolutions per minute as the angular velocity of the crank. And we only have a 3.5-inch crank and a 8-inch coupler, so there's going to be relatively little distance and change for the distance as compared to the velocity, which is going to be rather high, and acceleration, which is going to be even higher. But it checks out when you look at it, essentially. So you look at where you see a zero slope for the distance, and you can see that makes about a zero velocity. And when you have about a zero slope for the velocity, you find that that's zero on the acceleration. So it makes sense. And plus, where the slope is negative on the velocity, the slope is in the negative. Sorry, the acceleration is in the negative. And when it changes to positive slope, at that point, then the acceleration is positive. And it does the same for the distance for that changing to velocity. So just to show what it looks like when you run the code. So you press run on the program, you put in 3.5 for the length of the crank, 8 for the coupler, and the offset is 0. And the angular velocity that has to be in radians per second, just because it's convenient. I could convert it, but it's not necessary. And then it'll open up the plot in the background. It's overlaying them right now, but that's not too important. And it returns the min and max position, max velocity, and max acceleration. And to double check the work, we also simulated it in MATLAB. This is not exactly the same crank slider that we're using, since there's probably going to be a slot in the slider for an extra degree of freedom, so that it doesn't, when it bottoms out and changes direction for the coupler, it's not going to cause an excessive amount of force with retracting it back suddenly. And that just makes it so it's a little bit smoother. We're not really plotting the displacement, velocity, and acceleration of the slider. It's more so of the joint in the coupler that mates with the slider. So this is the animation running. This is the plots it generates. That makes sense that would be a pretty normal sine wave for the linear displacement. And this is also in time instead of angle, but that's also fine because they're pretty much interchangeable since it's a constant angular velocity for the crank. And you can see that the slope of this has a slightly forward bias, which when you go back to MATLAB, it's true there as well. And then for the acceleration, it has the same double hump. And we're also getting pretty much the same, well, not pretty much, the same values for the most part. You can see that the lowest acceleration is around 550 to 540, and when you check it on MATLAB, it's also negative 540. And the maximum acceleration is 269, which matches up with what MATLAB is providing. And the same goes for the velocity at the max being 39 and minimum being around negative 40. You can't tell exactly because this graph is rather zoomed out. And plus, this is much steeper on these curves just because the resolution of the for the scaling of the x-axis, but it's if you were to condense this down into however much this is, you'd be getting the same exact frequency. So yeah, hopefully that all makes sense. On to the rest of the presentation.